Hey everyone, so this is going to be lesson number 6 of this trigonometric identities and functions unit. We're talking in this lesson about double angle formulas. And so double angle formulas, they're a special type of compound formula where the angles being added are the same angle. So if we have two of the same angle, some angle alpha, we're now looking at sine, cos, and tan, our trig functions of double that angle. And what is true for all possible angles when we have a double angle. So to start, we're going to develop our double angle formula for sine. And we're going to use this idea of the compound formulas that we've already talked about. So 2 theta is really just theta plus theta. And what we had talked about for our compound formulas was sine of some angle added to some other angle is equal to sine of the first angle times cos of the second angle plus cos of the first angle times sine of the second angle. And so here, with both angles being theta, we're going to get sine of theta, cos of theta, plus cos of theta, sine of theta. So we have 2 sine of theta times cos of theta happening in both these terms. We have 2 of those terms, so we can just add those together. Cos theta sine theta is the same as sine theta cos theta. So we have 2 sine theta cos theta. And that is going to be our identity for this double angle formula. Sine theta equals 2 sine theta plus 2 sine theta times cos theta always. Saves us a little bit of time having to go through this whole compound formula. And so we'll look at a couple examples of rewriting trig functions. So sine of 4x, well 4x, that's just 2 times 2x. So we can rewrite that. Our theta in our double angle formula is going to be 2x. And so if we rewrite that, we get 2 times sine of 2x times cos of 2x. We could rewrite this sine 2x as well into 2 sine theta cos theta. And later we're going to talk about what the double formula is for cos 2 theta, or cos 2x. But for now, we'll leave it there, just showing you that even though it's not just 2 times something, this is really a double angle in disguise. Even though it's a quadruple angle by looks, we can also do it in reverse if we see a term like this, 2 sine of pi over 8, cos of pi over 8. Off the top of our heads, we don't know what sine pi over 8 is. We know sine pi over 4 because that's part of our special triangles. But we don't have an easy way to come up with these. We could use a compound formula, compound difference formula. But for now, there is an easier way. So this is 2 times sine of an angle times cos of an angle. So this just has to equal sine of 2 times that angle, 2 times pi over 8, which is sine of pi over 4. And again, we do know what sine pi over 4 is from our special triangles, so we could get an exact value from that, be 1 over the square root of 2. So let's look at our cos double angle formula. Come up with that. Cos of 2 theta. Again, that's just going to be cos of theta plus theta. And our compound formula was cos of our first angle times cos of our second angle minus sine of our first angle times sine of our second angle. So we get cos theta times cos theta minus sine theta times sine theta. So that's cos squared theta minus sine squared theta. So this is one way that we can write the double angle formula for cos. But using our trig identity, our Pythagorean identity, we can actually come up with a couple other ways to write this. So our Pythagorean identity, one of the examples was that cos squared theta is 1 minus sine squared theta. So if we sub that in, 1 minus sine squared theta, and we're subtracting sine squared theta, we get 1 minus 2 sine squared theta equals cos 2 theta. So there's another way to write this double angle formula for cos. And similarly, if we go back to our original and we use the Pythagorean identity that sine squared theta equals 1 minus cosine squared theta, if we sub that in, our cos 2 theta is going to be equal to that's still a cosine squared theta minus 1 minus cosine squared theta, or cos squared theta minus 1 plus cos squared theta if we get rid of the brackets, and cos squared theta plus cos squared theta is going to be 2 cos squared theta minus 1. So there's 3 different ways we can write an identity for cos 2 theta. And there's a couple examples of rearranging things. So cos of 1/2 of x, if we were to rearrange that using the double angle formula, this is not one where we're going backwards. We just have a single cos. So this is going to be our double angle here. So we need half of this angle is going to be our single angle. So half of 1/2 x is going to be 1/4 x. And then we can sub that into whichever one of the 3 that we choose. So in the completed lesson, they use this angle formula. Why don't we use the second one just to do something a little different? And you can check and see, but 1 minus sine squared theta, and our theta is going to be 1/4 x. So it could equal 1 minus 2 sine squared 1/4 x, or 2 cos squared 1/4 x minus 1, or as they say in the completed lesson, cos squared of 1/4 x minus sine squared of 1/4 x. The second one, to simplify, we have cos squared 3 theta over 2 minus sine squared 3 theta over 2. That looks an awfully lot like this cosine double angle formula. It's cos squared of an angle minus sine squared of an angle. So our angle theta is, in this case, is 3 theta over 2. That equals cos of 2 times our angle. So 2 times 3 theta over 2, that is just 3 theta. And finally, we can come up with a tan double angle formula. So tan of 2 theta equals tan of, we're going to use this exact same method of our angle theta plus our angle theta. And our compound formula for tan was tan of theta plus tan of theta. So tan of our first angle plus tan of our second angle, all over 1 minus tan of A times tan of B, where A and B are both theta. And now we can simplify this because our angles are the same. So tan of theta plus tan of theta is going to be 2 tan theta over 1 minus tan squared theta. And that is our double angle formula for tan. And again, we'll rewrite a couple just to see the mechanics of it. So tan 6x, here our double angle is 6x, so half of that, our single angle is going to be 3x. That's going to be equal to 2 tan of 3x over 1 minus tan squared of 3x. So again, our 3x is our single angle, and if we work backwards, 2 tan of pi over 6 over 1 minus tan squared of pi over 6. Our double angle, or sorry, this looks a lot like our double angle formula. So our theta is pi over 6. So 2 times pi over 6 is pi over 3. There's a couple examples that are also scratched out. I'll show you one just to show you what that actually looks like. So sine of 2 theta, we're going to use this method, and we're also going to use our 2 sine theta cos theta method for the angle theta equals pi over 4. So verify that this double angle formula actually works. So these should be equal to each other. Sine of 2 theta, sine of 2 times pi over 4 is equal to sine of pi over 2. Sine of pi over 2, or sine of 90 degrees, that is equal to 1. And our right side, using our angle pi over 4, sine of pi over 4 is 1 over root 2. Cos of pi over 4 is 1 over root 2. 1 over root 2 times 1 over root 2. 1 times 1 is going to be 1. Root 2 times root 2 is going to be 2. And 2 times a half, that equals 1. So left side does equal the right side. And this will work for any single angle. The sine of 2 theta is always equal to 2 sine theta cos theta. So it's an identity. It works for any angle that we put into theta. At the very end of this page, we have 2 more questions. So if cosine theta equals negative 2 over 3, and our angles between 0 and pi, what is the value of sine 2 theta? So sine 2 theta is, of course, equal to 2 sine theta cos theta. We don't know what our angle is, so we can't just plug it into this. So we're going to use the double angle formula. We know what cosine theta is. We know cosine theta is negative 2 over 3, but we don't know what sine theta is. Let's look at our quadrants, 0 to pi, so we're in either our all quadrant or our sine quadrant. And if cosine is negative, we have to be in this quadrant here. So negative 2 over 3 Our adjacent is going to be -2. Our hypotenuse is going to be 3. Our x value, we're going to the left, so it's -2. We can use Pythagorean theorem. So 3 squared equals 3 squared minus 2 squared is going to equal whatever this side is squared. 9 minus 4 is our x squared. 5 is x squared. So that x has to be the square root of 5, that unknown value. So our opposite is square root of 5. That means sine of theta, which is opposite over hypotenuse, is going to be root 5 over 3. So we can plug in sine of theta is root 5 over 3. Cos of theta was -2 over 3. 2 times -2 is -4 times root 5 is -4 root 5. All over 3 times 3 is 9. So our sine 2 theta has to equal -4 root 5 over 9. And if we're asked for an exact value, we're just going to leave it like that. There's no simplification we can do. We don't need an exact, or we don't need an approximation with decimals. This is how your final answer would be expected to be written. Can we see that all? Not quite. I apologize. So I'll leave that here just so you can see. And we're going to do one more example where we're told tan theta equals -3 over 4. And we're in the bottom right quadrant. We're looking from 3 pi over 2 to 2 pi. Calculate the value of cos 2 theta. So we need to see what is cosine 2 theta. Cos 2 theta, there's a number of different approximations we use. In the example, they use all 3. Let's do 2 cos squared theta minus 1. So our tan theta, we know already we're only looking in this bottom right quadrant. So we're going to have a negative y value. So our opposite will be -3. We have a positive adjacent value. We're going towards the positive x. So -3 over 4 was tan, so we get -3 and 4. Now, we need to know for cos what our hypotenuse is. So we're going to do 4 squared plus 3 squared is going to be our hypotenuse squared. 16 plus 9 is our hypotenuse squared. That's 25, and that means our hypotenuse has to be 5. Remember, hypotenuse is just literally the length of the triangle, so it's always going to be positive. It's the adjacent and the opposite sides that differ. So cosine is adjacent over hypotenuse. Adjacent over hypotenuse. Cosine squared, and all of that subtract 1. We have 2 positive numbers. Cosine should be positive in this quadrant, so that checks out. This -3 is what makes the sine and the tan negative, because both of them have an opposite in their ratios. So now it's just algebra. We're going to square our fraction. So 4 squared is 16. 5 squared is 25. Minus 1. There's no cancellation to be done, so 2 times 16 gives us 32 over 25 minus 1. Or, if we want to get the same common denominator, minus 25 over 25. And that will be 7 over 25. So now using these double angle formulas, we can easily do questions like this. We just need to remember our rules involving our quadrants. We're going to have to go back to grade 9, remember our Pythagorean theorem. But it's relatively simple. And if you look through the completed lesson, it shows the other two examples with the other two double angle cos formulas, and we get 7 over 25 every time. I just chose this one because it was a little bit cut off at the bottom, and we only have to deal with one trig formula rather than the cos squared theta minus sine squared theta. We have to deal with two. Maybe might make it slightly easier. In the end, it's probably about the same amount of work, but always good to try to think of how you can save yourself some work when possible. So that's the end of this relatively short lesson. Let me know if you have any questions, and you'll hear from me in the next lesson. Goodbye.